Hi everyone, welcome to my YouTube channel. In this video, we are going to discuss on tutorial 15, topic diffraction. And before we discuss the question, make sure you have done the question given in the description part below. And we are going to divide this video into two parts, part 1 and part 2. Okay, so first question. A narrow slit of width A is illuminated normally by monochromatic light of wavelength lambda. Calculate the angular separation between the first minima on either side of the diffraction pattern if A equals to 2 lambda and B, A equals to 4 lambda. Okay, for question A, the formula, for both question, the formula we're going to use is A sin theta equals to M lambda. So A is the separation of the slit. Lambda is the wavelength of the light, and theta is the angular separation. So we are going to find the angular separation theta. Okay, so now for angular separation theta here from the given diagram. So this is angular separation, and then the first minima is at here. Okay, this is central bright maximum. So the first minima will be here, which is m equals to 1, and the separation of the slit is A. So we substitute 2 lambda into the equation for A, angular separation given here, and sin theta is what we are going to find. M equals to 1, and lambda is the wavelength, so we can cancel out the wavelength, and we get sin theta equals to half and theta equals to 30 degrees. Okay, for look at the diagram here. So this is the theta, 30 degrees. But for the angular separation between first minima on either side, so that's mean another side for both here is the width of the central maxima, but the questions want angular separation. So between these two between the two first minima, top and the bottom, so we multiplied by 2. So 2 times 30 degrees, we get 60 degrees. Okay, so next question, what if we substitute the A 4 lambda into the equation? So we cancel the lambda both side, and sin theta equals to 1 over 4. So theta, angular separation, we get 14.5 degrees. For the separation between the first minima on either side, so we double the angle, okay, 2 times theta, and we get 29 degrees. Okay, so the angle become smaller when we increase the separation of the slit. Okay, now we go to question 2. Okay, monochromatic light of wavelength 470 nanometer is at normal incidence on a narrow slit. A screen is placed at a distance of 50 cm from the slit. The width of the central maximum is 3.8 mm. Calculate the width of the slit. Okay, so this is the slit. So we are going to find the A. So width of the slit or separation of the slit is A. And the width of the central maximum given 3.8 times 10 to the power of negative 3. Okay, from the diagram you can see here the meaning of width of the central maximum. Then the distance from the slit to the screen is 50 centimeter. Capital letter D. Okay, so the formula we are going to use is y equals to lambda d over A. And we substitute the y given here, but the y is from the center O to the first minima, so 0 to 0, 1. For y will be double the width here, so 3.8 times 10 to the power of negative 3. This one is a central bright maximum, so for the y it is measured from the O. to the first minima. So we divide by 2. Okay. And we substitute the wavelength, convert to meter, D 50 centimeter, convert to meter, and we can get A. Okay, so the A answer is 1.24 times 10 to the power of negative 4 meter. Okay, next, we can also, instead of using the formula y equals to lambda d over a, we can also use formula a sine theta equals to m lambda. Okay, so the sine theta, we can use trigonometric ratio to find the angle theta. And lambda and m equals to 1, so we substitute the value here. And the sine theta, we can use tangent equals to half of the width of central maximum, which is 3.8 times 10 to the power of negative 3 divided by 2 and divided by the d. So we use trigonometric ratio of tangent, opposite over adjacent. So the answer theta is 0.2177 degrees. So we substitute into here and we solve, we get A, same answer as the previous method, which is 1.24 times 10 to the power of negative 4 meter. Okay, question 3. Sketch the diffraction pattern produced by a narrow slit. And then describe the change in the pattern when the width of the slit is doubled and when the slit is illuminated with light with shorter wavelength. Okay, sketch the diffraction pattern produced by a narrow slit. So we can draw like this. Central bright, this is the central bright maximum, and don't forget the order on the left and right side. Okay, when the width of the slit is double, so using the formula A sine theta equals to lambda. So initial, let's say the width of the slit is A1. So the angle is sine theta 1 and equals to wavelength lambda. So this is equation 1. So the second equation, we double the slit, become 2A1. So sine theta prime, we put as theta prime. This is what we are going to find, what happened to the theta prime. Lambda will be the same. And we use ratio, equation 1 over equation 2. So we cancel A1 and lambda. And we get sine theta prime equals to half sine theta 1. Okay, so that's mean from this equation, we know that the width of central maximum becomes half. Okay, the sine theta prime here. So what happened is when the width of the slide is double, so the width of central maximum is half. Okay, next we look at the intensity of the light in on the screen. So intensity depends on the area, okay, directly proportional to area. So if the area of the slit, the light pass through the slit with we assume the slit as a circle area, so pi r squared. So intensity of the light that pass through the slit is directly proportional to the pi r squared. Okay, so we substitute the diameter squared over 4, because r is d over 2, so squared we becomes d squared over 4. Okay, so now we form two equation where the first one, the initial, let's say the intensity is I1. Okay, diameter of the slit is D1. Diameter of the, or the width of the slit is D1 is actually A1. So we can also substitute as D1 here. We use the symbol D1. Okay, for the second situation, the width of the slit is double, so we double it, becomes 2D1. Okay, so this is intensity 2. Intensity 2, we are going to compare to the intensity 1 for the first situation. Okay, now we use ratio. So what I1 over I2, so pi D1 squared over 4 over pi bracket 2D1 squared over 4. So we cancel pi D1 and the 4, and we get the intensity becomes 4 I1. So what happened when the width of the slit is double? Okay, the intensity at the center will becomes 4 times. Okay, I2 equals to 4I1. So this is what happened. What happened to the pattern when the width of the slit is double. Okay, next we go to question 2. Okay, question 2. When the slit is illuminated with light with shorter wavelength, so what happened? So we use the formula A sin theta equals to lambda. So from here we can see that if the wavelength is less or decreases, shorter wavelength, okay, what happened to the sin theta? Sin theta also decreases. This means that when the sin theta decreases, and it represent the width, the theta represent the width of the center bright maximum. So what happened? The width of the center bright maximum is reduced. Okay, so now we go to question 4. The pupil of an observer is of diameter 3.0 millimeter. The average wavelength of light is 550 nanometer. And what is the resolving power of the eyes of the observer? Net B. The tail lights of a vehicle is separated by a distance of 1.50 meter. And what is the maximum distance of the vehicle from the observer for the tail lights to be resolved? Okay, so this question is about the resolving power. So you are given the diameter of the pupil of an observer. So this is A, analogy to the diffraction, is a separation of the slit, okay, for diffraction pattern. So the pupil, the size of the diameter of the pupil is equals to A. The wavelength is 550 nanometer. So the resolving power theta. So the formula for the resolving power is 1.22 lambda over A. This is for the if the slit or the width of the size of the slit is a circle. So we use this formula. Theta equals to 1.22 lambda over A. Okay, if the opening of the slit is a circular shape. Okay, so now we substitute the wavelength and the A, 3 millimeter convert to meter. So we get the resolving power equals to 2.2 times 10 to the power of negative 4 radian. Okay, for question B, the tail lights of a vehicle is separated by a distance of 1.50 meter. So imagine this is the tail lights of a vehicle, example the car here. So the separation between these two lights is 1.50 meter. So what is the maximum distance of the vehicle from the observer for the tail lights to be resolved? Okay, so how far we can distinguish these two lights as the car move further and further away from us. Okay, so to represent it with the 2D diagram, so this is the observer and this is the distance between the two lights, 1.50 meter. Okay, so the resolving power will be theta here. Okay, so for theta, we can use the formula, this theta, and then okay, instead of using this one, the questions one the maximum distance of the vehicle from the observer. So this is the maximum distance observer from the tail lights of the vehicle. So let's say we use symbol capital letter D. Okay, so we can use for to find the resolving power theta here, we can use tangent. Okay, we can use trigonometric ratio. Okay, we can use trigonometric ratio. So tangent theta equals to opposite over adjacent. Okay, for the larger distance, so we can use this h over d. So h is 1.50 divided by distance that we are going to find in this question, and the tangent theta is equals to theta. Resolving power here is equals to theta for a very large distance. Okay, for a large distance, the tangent theta is approximately 2 theta in radian. So we can substitute a into here because we use our eye. Okay, so the pupil just now, our eye, we calculate the resolving power as 2.2 times 10 to the power of negative 4 radian. Okay, so now we cross multiply, we get the maximum distance is 6.8 times 10 to the power of 3 meter. Okay, for the tail lights to be resolved. Okay, now we've done for part 1, and we are going to discuss the part 2 question in the same topic, diffraction. Okay, question 5. The moon is 3.8 times 10 to the power of 8 meter from the earth. A telescope with an objective lens of diameter 12.0 centimeter is used to observe the surface of the moon. What is the diameter of a crater on the lunar surface which is just resolved using the telescope? So wavelength of light is 600 nanometer. So the distance Earth Moon is 3.8 times 10 to the power of 8. A telescope with an objective lens of diameter 12.0 centimeter is A. Okay, analogy to the um, diffraction diffraction of a single slit. So the rate the separation of the slit is the diameter of the objective lens. So we use symbol A. Okay, what is the diameter of the crater on the lunar surface, which is just resolved using the telescope? So diameter we use symbol D. Okay, so the wavelength lambda. Okay, how to visualize the given situation. So I help you by this drawing. So let's say this is the crater on the lunar surface of the moon. Okay, and this is the lens. Okay, so the theta here is the resolving power of the telescope theta. So lens diameter is A and the crater diameter is D, and capital letter D for the distance Earth to Moon. Okay, so we use trigonometric ratio to calculate this theta. Tangent theta equals to opposite D over adjacent is D, capital letter D, distance Earth Moon. So using the resolving power formula, so theta equals to 1.22 lambda over A. So we use this formula because the lens is a circular shape. So we use this resolving power formula. And for the D that is too large, okay, for the large D, so we can use approximation where tangent theta is equals to sine theta and it's equals to theta. So we can substitute theta D over distance between Earth Moon, capital letter D, into the equation here. Okay, so we cross multiply to get the diameter of the crater. So D equals to 1.22 lambda D, distance Earth Moon, divided by A. So we substitute everything and don't forget to convert to meter. All have same unit. So the answer, diameter of the crater is 2.3 times 10 to the power of 3 meter. So that's the answer. Now we go to question 6. A diffraction grating is ruled with 1,200 lines per millimeter. When monochromatic light falls normally on the grating, the first order diffracted beam makes an angle of 30 degrees with the normal to the grating. What is the wavelength of the light and what is the maximum number of diffracted beams that can be observed? Okay, so the diffraction grating, this has many slits. So the number of the between the slits is 1,200 lines. Okay, per millimeter. So we use D. This is D, symbol D, and then angles 30 degrees for the first order, which is m equals to 1. And we are going to find the wavelength. So the formula for diffraction grating, we use d sine theta equals to m lambda. Okay, so and d is the 1 over n. For the distance of one slit, we have many lines, which is 1,200 lines for 1 millimeter. So this is 1 here means 1 meter. So we need to convert the millimeter to meter. Okay, so now we substitute d 1 over n. So convert to convert to meter. For millimeter is 1 times 10 to the power of negative 3 over number of lines or slit is 1200. Okay, angle 30 degrees. M order is first order, so M is 1. So we get lambda equals to 4.17 times 10 to the power of negative 7 meter. Okay, now question B. What is the maximum order of diffracted beams that can be observed? So to find the maximum number, the maximum angle of light cannot larger than 90 degrees. So for the light to reach the screen, so the angle must not exceed 90 degrees. So therefore, sine theta must be less than 1 because sine 90 degrees is equals to 1. Okay, so sine theta from the equation here, d sine theta equals to m lambda and sine theta equals to m lambda over d. So we substitute into here, we get m lambda over d less than 1. And cross multiply lambda over d to other side become d over lambda. And we substitute the d which is equals to 1 over n. And the 1 is in meter, so you convert millimeter to meter. And n is 1200 lines. And the lambda calculated in A is 4.17 times 10 to the power of negative 7. So we get m here must less than 2. So less than 2, if equals to 2 cannot, the light cannot be perpendicular to the cannot larger than 90 degrees like said just now. So this is the diagram to imagine. So this light cannot 90 make angle theta 90 degrees because it cannot reach the screen here. So therefore m must less than 2, which is m equals to first order, m equals to 1 first order. So the second, third and fourth is not logic. The light cannot reach the screen. So the number of diffracted beams will be 1, 2 and 3. Don't forget to add the negative order. So 2 plus 1, the positive order and the negative order. Positive 1 and negative 1 and plus the center bright maximum. So 2 plus 1 we get 3 maximum 3 number of diffracted beams. Okay, so now we go to question 6 or question 7. A beam of light that consists of the wavelengths 400 nanometer and 600 nanometer is incident normally on a diffraction grating that has 750 lines per millimeter. Calculate the angles of division for the diffracted beams and draw a sketch to show the diffracted beams and label on each beam its wavelength. Okay, so to calculate the angles of division theta, we use the formula. This yang sin theta equals to m lambda and d is 1 over n. So for m equals to 1, the lambda for lambda 400 nanometer, so we substitute into the equation here, and d is 1 over n, so 750 lines per millimeter. So 1 millimeter converts to meter is 1 times 10 to the power negative 3 meter. And 750 lines, sine theta 1 prime. So let's say we call the angle, the first angle for M1 is sine theta 1. Okay, substitute the wavelength and we get the angles of division is 17.5 degrees. Okay, next, for wavelength 600 nanometer, for M equals to 1, we use the same formula and the same diffraction grating, and we get theta 1 26.7 degrees. So we name this as theta 1 prime prime to show the difference between these two angles of division. So use different symbol. So here we use theta 1 prime and theta 1 prime prime. Okay, so we do the same for M2 and lambda 400 nanometer. 400 nanometer. So we substitute into the equation d 1 over n sine theta equals to m lambda. Okay, so we get theta 2 36.9 degrees. And we do the same for lambda 600 nanometer, M2. Okay, we get theta 2 prime prime 64.2 degrees. Okay, we continue doing for M3. For M3, lambda equals to 400 nanometer. So we substitute into the same equation, we get theta 3 prime 64.2 degrees. So still the beams can be diffracted and reach the screen. Okay, because 64.2 degrees. So we try for M3, which lambda 600 nanometer. Okay, so this one is for M3 lambda 600 nanometer. So we get the angle larger than 90 degrees. So this one is not logic. So for M3 and order 3 for lambda 600 nanometer is not possible. Okay, so these are all the possible diffracted beams. We can see the patterns on the screen. Okay, so theta 3 is not possible. So this is all the angles of division for the diffracted beams. Okay, now we are going to question B. Draw a sketch to show the diffracted beams. And we are going to label on each beam its wavelength. Okay, so these are all the angles for the wavelength 400 nanometer and 600 nanometer. So the order is until 3. Okay, so this is the diffraction grating and the light incident to the diffraction grating. So center bright maximum is at M0 for both 400 nanometer and 600 nanometer wavelength. Okay, for 400 nanometer, the angle is 17.5 degrees. Okay, and then for 26.7 degrees, it will be higher up. Okay, we label it M1 600 nanometer. Okay, and next 36.9 degrees for M2 400 nanometer. And for 600 nanometer, so we label here the angles is 64.2 degrees. So we draw higher. And lastly, for the M3, for M3 64.2 degrees at the same the pattern is at the same angles. So we draw at the same angles here. We label on the same lines to show the diffracted beams. So M3 400 nanometer. And don't forget we have a negative order. So all this is the positive order. And for negative order, we do the same. Okay, so that's the sketch to show the diffracted beams. Okay, done. Question 7. Okay, now question 8. White light of wavelength 400 nanometer to 700 nanometer falls normally on a diffraction grating ruled with 6,000 lines per centimeter. Calculate the angular width of the second order spectrum. Okay, formula is d sin theta equals to m lambda. D is 1 over n. So for M2, for second order here, M2 and lambda 1 is 400 nanometer. So we substitute into the equation 600 lines per centimeter. So 1 centimeter convert to meter, we get 1 times 10 to the power of negative 2 meter. Okay, so we get theta 2 equals to 28.7 degrees. Okay, for 700 nanometer, so second order, we get theta 2 57.1 degrees. But the questions want angular width. So be careful, angular width of the second order spectrum. So that's mean the angular width will be 57.1 degrees minus 28.7 degrees. We get 28.4 degrees. So this is the angular width asked by the question. Okay, done for question 8. Okay, so that's all for tutorial 15 diffraction topic, and we've done for both part 1 and part 2.